Hi, my name is Deepak, currently working in TCS IT System Engineer role. I have mentored over hundreds, nearly thousands of students to master their technical skills. The topic for the video is BFS algorithm. BFS is in graph traversal algorithm. It is similar to the level order traversal in trees. BFS algorithm tends to traverse the nodes of the graph level by level. Okay, here we'll understand the BFS algorithm in depth. We'll try to identify the implementation of the algorithm. Okay, we'll do it. Okay, let's get to it. Let's take an example. Okay, this is a one based index graph. We have two types of graphs: zero based index graphs and one based index graph. Okay, now BFS, the full form of BFS is breadth first search. The term what is meant by breadth? Breadth determines the distance from the currently selected node or the initial starting node to the traversing nodes, and that distance determines the level in which these nodes lie. Let's take for example, let's suppose our starting node is node 1. Okay, so the distance from this node 1, let's suppose this is our starting node, the distance from node 1 to these 2 and 3 is 1. Now and at what distance the node 1 is? It is at 0 distance. Okay, what are the nodes at distance 1? That is 2 and 3. Now what are the nodes at distance 2? Those are 1 plus 1 2. Okay, so at distance 2, that is 4, then 5, okay, 8, then 6, so then 6. Okay, what are the nodes at distance 3? That is 7. Okay, that is at 7. Now as we can see in the graph that at distance 0, node 1, distance 1, like distance 1 2 3, at distance 2 4 5 8 6, and at distance 3, that is 7. The distance from the currently starting node is known as the level of the node. Okay, level 0 is 1, level 1 is 2 3, level 2 is 4 5 8 6, and level 3 is 7. Here, here it is. This is 0th level, this is first level, this is second level, and this is third level. The traversal of the graph in this level manner, in this level wise, is known as the breadth first search algorithm, or the algorithm which leads us till this is the breadth first search algorithm. Now how do we achieve it? Let's understand that. Okay, let's take on the graph the algorithm, the fundamental of algorithm. How does it work? Okay, so we'll understand that. Suppose 3 4 and suppose 5. Take it this. Okay, the fundamental of the algorithm is we tend to traverse the neighbors, the very next neighbors, very nearest neighbors, the currently selected node, and we traverse the rest nodes of the graph in the same manner by traversing the nodes of the already selected nodes. Okay, neighbors of the already selected nodes. Let's try to understand it. Let's suppose my starting node is 1. Now I'll check what are the neighbors of 1. That is 2 and 3. Okay, I took the node 1. Now what are the neighbors of 1? 2, 3. We started with node 1. Okay, the neighbors of 1 are 2 comma 3. Now what are the neighbors of now we'll start with the further graph. The further graph is 5. How do we traverse it? We traversed 1, 2 3 are the neighbors. Now we'll traverse the further graph by traversing the neighbors of the already selected node, that is 2 and 3, and in the same order. In the same order, like if we take 2 comma 3, like 2 first and then 3 here as we did, so we'll take traverse the neighbors of the 2, that is 5. Do we have 3, like the do we have any other neighbors of 3? No, because we will also keep a track what all nodes are already visited. The already visited nodes will not be traversed again. Okay, so that each node is visited only once. That is the main goal of us, that we visit the each node of the graph only once, and in the level wise order. Okay, and that would be the level BFS traversal of this graph. We understood this much? Okay, let's try to understand how do we achieve it. Okay. Okay, how do we achieve this level order traversal or BFS algorithm by traversing the neighbors of the currently selected node, and then what all nodes are already selected, traversing their neighbors in the same order the nodes they are selected. So let's try to understand this. Let's take one graph. Okay, let's take one. I'm taking again one base index graph. Two, three. Let's suppose seven, eight, okay, six, five. Let's take suppose four. Okay, one, two, three, four, five, six, seven, eight. Okay, okay. And to achieve this, uh, we'll take queue data structure. The data structure which is used to traverse the nodes in an order is the queue data structure. Okay, so our starting node is 1. We took the 1, or let's take something else this time. Okay, let's take 2. Starting node is 2. Okay, now starting node is 2. We enqueue it, and now we traverse until our queue is empty. Okay, we will also maintain one array named visited, where now we have a one based index graph, so zeroth indexing won't of matter to us. Okay, it won't matter to us. And we have nodes delayed, so we need a 9 size array so that we could have 8 as a number, 8th index to be used in. Okay, 0 1. Okay, and initially all are unvisited. Okay, so we mark them 0. Okay, now the starting node is 2. We enqueue it. Now we traverse the graph until all nodes are traversed. Okay, we dequeue it. We take it 2. Now we explore all the nearest neighbors to the 2, that are 2, 1, 8, and 7. Now we will push them inside the queue in the very same order, that is 1, 7, 8. Okay, we took it. Now 2 is done. Before that, when we are dequeuing the element that we did 2, we dequeue the queue, and we check the 178. We should mark it visited. Okay, so it's visited now 1. Okay, now the next node which we will process is 1. As remember what I said, we will traverse the further graph by traversing the neighbors of the already visited nodes in the same order. Okay, so we visited all these nodes, like we processed these, not visited yet, we did not mark them officially visited. We just took them that these nodes should be visited further, or these nodes should be processed further, because these were the neighbors of the 2. Okay, now we'll take 1, we'll enqueue it, we'll mark it visited. Okay, sorry, I marked 1 by mistake visited. It was 2 that has to be marked visited. Now we marked 1 as visited. Okay, and what are the neighbors of 1 now? That is 2 is already visited. Okay, so 3 is the neighbor. The only neighbor of the 3 of the 1 is 3. We'll push it. Okay, now we visited the 1 as well. Now we'll enqueue the dequeue the 7. We'll mark it visited first. Okay, now what all the neighbors of 7 are? 2 is the neighbor, but we don't have any other neighbors of it. Okay, so we'll not there are no further neighbors to push it inside. Okay, now the next 8, we'll process 8. We dequeue it, we'll mark it visited. Neighbors of 8 are 2 was the neighbor, but it's already visited, so 4. We'll take it 4. We'll push it inside. Okay, now we traverse the graph of the neighbors of the 8. Now we'll like dequeue 3. Okay, like we'll get the 3. Now we'll explore what all the neighbors 3 has. Before that, we'll mark 3 as visited. Okay, what are the neighbors of 3? That is 1 already visited, 6 and 5. It is 6 and 5. We'll push it inside, push them inside 6 and 5. Did. Now we'll take the 4. Okay, we'll mark it visited. Neighbors of 4 are, we don't have any neighbors. 6 was there, 8 was there, but they're already visited, so we don't have any other neighbors. So that's done for it. Now 6. Okay, we took 6 and 5, right? Okay, now mark it visited. What are the neighbors of 6? We did have the neighbors 3 and of 6, 3 and 4, but they are already visited. So we don't have any other neighbor of the 6. There are no further neighbors. Now we'll go with 5. We will dequeue it, like we'll get it out. We'll mark it visited. We'll explore what all neighbors it has. Does it have any neighbors? No, it does not have any neighbors. Like it has 3 as a neighbor, but it's already visited. And that's how our graph is traversed. Okay. The first node which we marked, that was 2, okay, it was visited. Then we went 178, then we went 3, then we went to 4, 6, 5, and that's it. That's how the graph is traversed. Okay, and that's how the BFS algorithm works at the core level, the fundamental level, by using the queue data structure and the visited by taking an array of the size of the number of nodes. Okay, that's how it works. Let's we understood the implementation. Let's write a pseudocode of it and let's finish it off. Okay, that's right. As we already discussed, that we will traverse the graph, or we'll continue the traversal until our queue is not empty. Okay. So first of all, through okay, let's suppose there is a BFS function. We'll take a visited array. Okay, of size 9. We'll take the, like, let's take it for example of size n plus 1 comma 0. Like, just a minute. N plus 1 comma 0. Now n plus 1 in case it is a 1 based index graph, and n in case it is a 0 based index graph. Okay, right. Now what else we need? We need the starting node, Sn. Okay, Sn means starting node. Okay, what else do we need? We need the data where our graph is stored. Now we have two ways to store the graph's data, that is either we use a matrix or we use a adjacency list. For the time being, I'm imagining I'm writing a function for adjacency list. Okay, it is kind of the same. It's very same. Like you you explore the neighbors of the current node. You can use a matrix or you can use a adjacency list. It's both the same. Okay, edge edge list. Okay, now we'll define a queue data structure. Hmm. We'll define a queue data structure. Okay, we will push it the starting node. Okay, now we'll continue the traversal until our queue is not empty. Remember the point, the most important point. Okay, now we will dequeue the first most element inside. Okay, now what are we doing here? We are trying to explore those elements which are already taken, and that too we are trying to process them in the very same order, the order in which they are taken or pushed inside the queue. Okay, so for that purpose, what is the queue? First in, first out. So in whatever order we are pushing them, in the same order they'll come out. Okay. Okay, so we'll take the node q dot first. Okay, and q dot remove the first element. Okay, it's just a pseudo code. Now we will traverse the adjacent nodes, the very nearest or the most nearest nodes of the currently selected node. Now what is the currently selected node? It is node. Okay, this is the currently selected node. Now we'll traverse the very next neighbors of it. Okay, so for each we'll use a for each loop here. Okay. Mm, before that, we will mark the node visited. Like we are setting it to 1. Okay, and we'll explore all the nodes. Now if the node is not visited, if the node is not visited, then only we will enqueue it, we'll push it inside the queue. Okay, queue dot push n. And if it is visited, we will not proceed with it because it's already visited, and visiting the already visited node will introduce the infinity inside the graph. Okay, and that we don't want, or continuous cycle repetitions. Okay, and that's it. That's how our BFS algorithm works. Yeah, that's all. Okay. BFS is the most fundamental algorithm and most required and important algorithm in graph traversals after the DFS algorithm. There are many algorithms inside the graph which are just little advanced versions of the BFS algorithm, a small modification in it, and we have a new algorithm with its own name, like the Dijkstra's algorithm, where we just instead of using the simple queue, we use a priority queue there based on a heap. Okay, and by adding a few more parameters to that priority queue, we have our Dijkstra's algorithm, which is the shortest path finding algorithm. And not just that, that BFS algorithm, instead of its standard implementation, we can use it inside this just the same format. We can use it inside the matrices as well. Okay, like not the matrix arrangement of the graph, but the matrix itself is representing a graph. Okay, till certain node, till certain row column position, it is a graph, and after that we have a water, something like island problem. Okay, so such problems, root and oranges problems, these kind of problems are easily solvable using the breadth first search algorithm. Now coming to the time complexity of the BFS algorithm, it is v plus e. Now why v plus e? V means v represents the number of vertices and e represents the number of edges. Of course, we are visiting the each node only once, like, according to the traversals which we did till now. Okay, let's say 1, 2, 3, 5. Okay, each node is traversed only once, but then y plus e, like y plus e. The reason is here. We are checking whether that node is visited or not visited, and it leads us to explore all the possible edges or all the possible connections of the currently selected node, and that leads us to the time complexity of order of v plus e. That's it. Thank you.